Acceleration of a particle in polar coordinate. Acceleration of a particle in polar coordinate. Acceleration of a particle in polar coordinate. The acceleration of a particle in plane polar coordinate r theta is given by the acceleration of a particle in the acceleration of a particle in plane polar coordinate r comma theta is given by vector a equal to double derivative of r minus r derivative of theta square unit vector r plus r double derivative of theta plus 2 derivative of r derivative of theta unit vector theta equal to ar vector ar plus a theta vector, where ar is the radial acceleration, where ar is the radial acceleration and theta vector a theta is the transverse acceleration, transverse acceleration. Writing the two independently, we have vector ar equal to vector double derivative of r minus r derivative of theta square unit vector r and vector a theta equal to r double derivative of theta plus 2 derivative of r derivative of theta into unit vector theta. Multiplying the above relation by m mass of the particle, we have m ar vector equal to m double derivative of r minus r derivative of theta square unit vector r equal to the function of fr unit vector r and m a theta vector equal to m r double derivative of theta plus 2 derivative of r derivative of theta unit vector theta equal to function of theta unit vector theta. This is the equation number 1 and this is the equation number 2. This is the equation number 2. Where fr unit vector r gives the radial force along the direction of increasing vector r, and f theta unit vector theta the transverse force. Which force? Transverse force along the direction of increasing theta. From the equation 1 we have from the equation 1 we have m double derivative of r minus mr derivative of theta square equal to fr function. This is the equation number 3. This is the equation number 3. This equation is known as radial equation of motion. This equation is known as radial equation of motion, radial equation of motion. In the case of a central force F theta unit vector theta, which represents the components of force depending upon angle, is 0, as the force only acts along the direction of r and is denoted by Fr. To prove that F theta unit vector theta is 0 for a central force. Because in the case of central force F theta unit vector theta, which represents the components of force depending upon angle, is 0. Depending upon angle is 0, as the force only acts along the direction of r and is denoted by Fr unit vector r. The magnitude of angular momentum, the magnitude of angular momentum J equal to mod of J equal to m r square unit vector theta. This is the equation number 4. And dj by dt equal to 2mr differentiate of theta plus mr square double derivative of theta equal to mr common, and r double derivative of theta plus 2 derivative of r and derivative of theta equal to 0 as in the case of central force J equal to a constant, and therefore as in the case of a central force J vector J equal to a constant, and therefore dj mod of dj vector upon dt equal to 0. Hence equation number 2 can be stated as f theta unit vector theta m equal to m r double derivative of theta plus 2 derivative of r derivative of theta unit vector theta equal to 0, r m r double derivative of theta plus 2m derivative of r into theta equal to 0. This equation is known as equation of motion of theta coordinate. This equation is known as This equation is known as equation of motion of theta coordinate. coordinates. Okay, thank you.